Hello, this is for lesson 3.2, exponential functions. Now this section, you're going to need to have a scientific calculator to evaluate some of these answers in when we get to the application problems on exponential growth and decay. And graphing calculator will also be helpful because we will be graphing some of them. After finishing watching this video, taking notes, the classwork that goes with this section is a Canvas quiz. I did make a Canvas quiz. It's called quiz, but it's going to count as a daily problem grade. And then just wanted to show you the notes also posted on Canvas if you want to download this and go through this with me. But the Canvas quiz has about 10 problems. I can preview the quiz for you just real quick. Just about transformation, a couple of these word problems that we're about to go over together, okay? You do have 3 attempts on this Canvas quiz, and I will record the highest score. So to keep taking it, you have until this Sunday to finish this 3.2 quiz, okay? All right, let's go over that notes together then. I may need to stop and kind of have a separate video on going over the application problems, but let's first talk about what exponential functions are, because just because you have a function with an exponent, it doesn't mean they're exponential functions. For example, if you have y equals x squared, well, we don't really call that an exponential function. I know it has a power of 2, but this is a quadratic function, right? This is a quadratic function. What makes it an exponential function? Something like this. If you have y equals, well, 2 raised to the x power. If you have if you have a variable, the x is somewhere in your exponent, well, those are going to be the exponential functions. And we're working with them. We're working with the exponential functions and their inverse function called logarithmic functions in Unit 3. In the first section, well, 3.2, we're just going to work with exponential functions and some of the application problems. All right, let's read the definition of exponential function. Let b be a constant real number such that b is greater than 0. Circle that part. You have to have the base to be greater than 0, and base cannot be equal to 1. Imagine raising something, and that's something, 1 to the x power. I mean, what's that going to be? If you take a look, if you do, say, 0 power, first power, second power, third power. Suppose that we're plugging in 0, 1, 2, and 3 into x. That's going to be 1 to the 0 power, 1 to the first power, 1 and 1 squared, and 1 cubed, right? And so on. And these will all just come out to be 1. So the base cannot be 1, guys, okay? So 1 is not allowed to be a base of an exponential function. It has to be a number greater than 0. No negative numbers. Then for any real number x, a function of the form f of x equals b raised to the x power is called an exponential function of base b. So I got a couple examples that are actually, these 3 are exponential functions. Let's take a look at these 3 together. The base is 3, and 3 is getting raised to x power. If you write a xy table real quick, starting with x equals 0, 1, 2, and it can be a negative input. The x can be any number, right? But if you evaluate this, we're doing 3 raised to the 0 power, 3 raised to the first power, 3 squared, and so on. By the way, anything to the 0 power is 1, okay? This one will be 3, this one will be 9, and so on. Now, this one will be considered an exponential growth. Why do you think this is a growth function? Look at the numbers that we got, the y values. As x increases, the y values are also increasing, right? Exponential growth functions have base that is greater than, well, I think, hold on a second. Will I be able to go over those? Yeah, I think I'll go over those down here. But to be a growth function, the base has to be bigger than 1. The base has to be bigger than 1. And notice the base for this function that we just looked at is what? 3, right? So if that base is greater than 1, we're going to call that a growth function. But let's talk about the growth function and decay function a little bit later when we get to the second page. The second one, g of x, that's another exponential function. The base is 1/3. Base is 1/3, so base can be a fraction as long as it is greater than 0 and not equal to 1. Now this one later, we'll see that this is an exponential decay function, okay? All right, what about this one? What's the base? Base is square root of 2. Are we allowed to have that? Yes, that's okay. We're just going to raise square root of 2 to x power. And these three are just great examples of exponential functions. But let's look at these three that are not exponential functions. Well, this one, m of x equals x squared. Base is not constant. And that's really a quadratic function, right? That is not an exponential function. Look at the second one. N of x equals negative 1/3 to the x power. Base is negative. To be an exponential function, you know, base has to be a positive, it can't be 1, but it has to be positive. All right, last one. P of x equals 1 raised to the x power. Base cannot be 1. So, just couple examples of what are exponential functions, and we also saw a couple of the other ones that are not considered to be an exponential function. But let's graph two exponential functions and talk about their domain and range. First one, example 1. Let's graph f of x equals 2 raised to the x power. I know you have a graphing calculator and feel free to use it. We do have it if you want to use it. But I'm just going to go ahead and pick some values and I will graph it by hand, okay? Now, f of x equals 2 raised to the x power. I'm just going to pick any x values, and that kind of talks about the domain. Domain of an exponential function is going to be always all real. Why? Because there's really no restriction on what we can make to be an exponent. We can raise 2 to the any power if we want. Starting with, I want to show you that it doesn't really have to be a positive number. X can be 0, x can be 1, x can be 2, but x can also be a negative number. We are allowed to raise 2 to the negative power. Let's go ahead and do those by hand. So, the y value will be, remember base is 2, right? 2 raised to the negative second power. What's that going to be? That is 1 over 2 to the positive second power. And that is simply 1 over 4. And because I'm going to graph it, I'm just going to convert it into decimal. That's about quarter. All right, next one. 2 raised to the negative first power. What's that going to be? 1 over 2 to the first power. And that's simply 1/2. So I'll plot 0.5 on my graph, okay? Next one, 2 to the 0 power. What's that going to be? That's just going to be anything to the 0 power is 1, okay? 2 to the first power is 2. And 2 squared is going to be 4. Now, if you want to continue, you notice the y values are getting big very quickly. 2 to the third power is 8. And if you think, the next number will be 2 to the fourth power, which is going to be what? 16. So from that point on, it's just going to double really, really fast. Okay? Now, let me go ahead and plot these and have a sketch of f of x equals 2 to the x power. These are going to be negative 2, 0.25, negative 1, 0.5, 0, 1, 1, 2, and so on. So plot these. Maybe just one more, 3, 8. I'll plot these points and then I will sketch a graph. 2 to the left. Let me just make up 1, 2, 3, 4, 5, 6, 7, 8. First one, negative 2, quarter point up, about right here. Next one, 1 to the left, halfway up. Next one, 0, 1. 2, 1, 2. And then 2, 4, 1, 2, 3, 4. So I'll have a point right here. And maybe the last one, 3, 1, 2, 3, 4, 5, 6, 7, 8. So I'll have my last point about right here. I mean, it's going to keep on going up, right? You know it's going to keep on going up. It's just, I don't have enough room here. Now, I'm going to go ahead and connect the dots here, okay? Take a look. To the right, it's going to go up like crazy, right? Now, imagine it's going to keep on going up. So, do we have an upper bound in this function? It's going to keep on going up. So, to the range, when we talk about it later, we'll talk about it right now. It's going to go all the way up to positive infinity. But take a look. Imagine taking something, because to the left side, we're really taking half, right? Because I think you can see the pattern here. As you are going up, you're just doubling. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, right? But imagine going backward. Imagine going backward this time. 16 divided by 2 is 8, 8 divided by 2 is 4, 4 divided by 2 is 2, 1. What? 4 divided by 2 is 2, and half of 2 is 1. You continue this. You really continue this. Half of 1 is 1/2. Half of, 0.5 is 0.25. Keep on taking half, 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 and half, and half. How small can we get? Can we go to the negative side? Not really, right? Now, this is, what we just kind of talked about is it's going to get really, really, really close to 0. Because you keep on taking half of something, like half of a bread, half of a, keep on taking half of this bread. Are you going to have a negative amount of bread left? Never, right? You mean the crumb's going to be so small, it's going to be like 0, but it will never really be 0, and it will never really go down to negative. So what I want you to do is I want you to draw a tail that is getting really, really, really close to 0, the horizontal well, I said it. We have a horizontal asymptote, guys. Horizontal asymptote is at y equals 0. I want you to sketch that with the dotted line. We have a horizontal asymptote at y equals 0. Because as you keep on going to the left, as x approaches negative infinity, f of x is approaching 0. So horizontal asymptote is at y equals 0, and all the exponential functions will have a horizontal asymptote. Now let's write the range, okay? Let's write the range. Now to the right side is going up to the positive infinity, but what's the smallest y value that we're trying to get to? It's 0, right? So do not draw bracket 0 infinity, because it's never going to touch 0. It's going to get really, really close to 0, but really never touch 0. So that's how you graph an exponential function. By hand, just really plotting points, but you do want to remember that we have a horizontal asymptote at y equals 0. Now, let's graph the other one. But before I go there, I want you to add something over here. Now, call this function exponential what? It's going up, right? Growth. Now, the easiest way really is to determine whether it's a growth or decay is really you graphing it. And then if it's going up from left to right, it's going to be an exponential growth. But the second one that we're about to graph together is not going to be an exponential growth. That's going to be a decay function. Let's see how that one's a little different, okay? But first of all, do want you to know that the domain of any exponential function is always all real. So don't even think about this. You know why already. You know because we can raise base to any power if we want. There's no restriction on what can be the exponent of this expression. Now, I'm going to go ahead and just pick a couple, values again. Maybe like 0, 1, and 2. But I do want to test some negative values for my x's. So let's go ahead and plug it into the function. The function is for you to raise 1/2 to that exponent. So I'm doing 1/2 raised to the negative 2. Well, what's that going to be, guys? What's that going to be? Well, it can be a little bit messy. I mean, this is really 1 over 1/2 squared, right? Or if you just want to use the reciprocal rule, oopsies, that's just going to be 2 raised to the positive half. That's just going to be 4. Now, if you want to use your calculator for this, I am fine with it. So I do have a calculator app that I downloaded. I can try to type this in. Let's type in 1/2. Where's the fraction? 1/2 raised to the, what was the exponent? -2, right? If you type that in, they're going to give you 4. So that's okay if you want to use your calculator to evaluate. But you do know your exponent. Oh, what's that? 1/2. I'm doing the next one, guys. Raised to the -1st power. And that's going to give us, what do you think that will give us? 2. So this one will be 1/2 raised to the -1st power, which is simply 2 to the 1st power. And that's 2. And from this point on, it's going to be a little bit easier, right? 1/2 to the 0 power, anything to the 0 power is 1. 1/2 to the 1st power, well, that's just going to be 1/2. 1/2 squared, what's that going to be? That's going to be 1/4. So plot these 5 points. Let's plot these 5 points and let's see what it looks like. First one, I have 2 to the left of 4. 1, 2, 3, 4. Next one, 1 to the left up 2. 0, 1. Ah, I see something is going down from left to right. Next one, 1, and then just go up 1/2. Next one, 2, and then go 1/4. Now look at the pattern, because I want you to notice the pattern here. Now it was going down like whoosh this way, right? But do you kind of see it levels off, like, because you'll see why. We're taking 1/2 every time, right? Let me use a different color. 1/2 of 4 is 2. 1/2 of 2 is 1. 1/2 of 1 is 1/2. 1/2 of 0.5 is 0.25. You keep on taking 1/2. Take 1/2, right? Same idea, really. If you keep on taking 1/2 of any number, you keep on taking 1/2, you will never really reach 0. You just get really, really, really close to 0, but you are never allowed to go cross that 0 line, or it's not going to go down to a negative. You still have something. So we still have a horizontal, asymptote at y equals 0, because as x approaches positive infinity, our f of x is approaching 0, right? So let's talk about the range here. Range. How high up does this graph go? The highest it goes is positive infinity, right? But the range, I mean, the lowest number that it's going to try to get to is 0. So notice without any vertical translation, we didn't move these two graphs up or down at all. The domain and range really came out to be the same. They just look different, right? Now, if you have a graph, you graph an exponential function, and the pattern is going down from left to right, do write down these are exponential what? Decay. So this function is an exponential decay function. So we'll look at how we don't really have to graph it to see whether it's an exponential decay or growth. I believe in the very second page. So that's how you can graph too. You don't really need a graphing calculator to graph these exponential functions. But if you have one, use it, okay? I'm going to y equals, and let me just type in what I have. The first one was y equals 2 raised to the x power. Let's graph it. My zoom is all kind of messed up, so maybe I can change the zoom a little bit. Window, I may just do, is there any way for me to do zoom standard? This is a new app that I downloaded. I don't think I'm too familiar with this. Maybe I'll just use Desmos. Where's my Desmos app? All right, let me graph both of them. Y equals 2 to the x power. Well, that's the red one, right? That's the one that's going up from left to right. That's the exponential growth. Let me do the other one. Y equals, the other one had a base of 1 over 2. But we were raising that to 1/2 power. that's getting raised to, not 1/2 power, x power. So the blue one is going down from left to right. But as you can see, both of these lines are going up forever, but they're not really going down below y equals 0. So we can say that both of these functions have a horizontal asymptote at y equals 0. All right, so do feel free to use those graphing utilities if you have them. Let's go over transformations. And then I'll come back and record another video on these application problems. These are going to be actually the easier ones. All right, let me read these important facts about graph of an exponential function. The graph of an exponential function defined by f of x equals b to the x power, where you know already that b better be positive and b can't be 1, has the following properties. Next, the first one, if b is greater than 1, it's an increasing exponential function, so we call them exponential growth function, okay? If the base is bigger than 1, then it's called an exponential growth function, okay? What if the base is smaller than 1, but it still has to be greater than 0, right? So what kind of numbers fit in this interval? What kind of numbers? Numbers like half, right? Or what else? 3/4, right? 6/5, well, not 6/5, but 6/7. Anything that is smaller than 1, but that's still positive. When you have a case like that, when the bases are, it can be fraction, or maybe you can have like 0.25 or 0.78. All these bases will create an exponential or decay exponential function that we call exponential decay. So if you're ever... And I love to trick people. Like I give sometimes something like this. Y equals 4/5 to the x power. Everybody knows, and a lot of people just kind of go with this rule. Oh, if the base is fraction, it must be decay. Well, this one is decay. But what if I make it like this? Y equals 5/4 to the x power. I mean, some people say, oh, that's a decay because 5/4 is a fraction. But look, because 5/4 is actually greater than 1, this will be a growth function. So just be careful. You're just looking at the base to determine whether it's a growth or decay. But I do have the Canvas quiz problem that kind of asks you which one of these are growth or decay. And I want you to just be careful, okay? All right, so that's how you can tell whether it's a growth or decay. Couple other important stuff that we kind of already talked about. Domain of any exponential function is always all real, okay? Because, like you've seen, we can raise a constant to any power if we want. All right, the range, this is before we transform it or translate it vertically. Range is going to be 0 to positive infinity, okay? But those will change. If you have y equals 2 to the x power, say that we're going to translate this up 5 units, okay? Because, adding 5 outside will move the graph up 5 units, right? So what will happen? We're going to have a regular graph. But that graph will be translated 1, 2, 3, 4, 5 units up. So your graph will look something like that. So the range will actually be from 5 to infinity, not 0 to infinity. So number 3, the range really applies to functions that's not translated vertically, okay, yet. But if you have a piece added to it or subtracting, then the range will change and we will look at them, okay? All right, the line y equals 0, that x-axis is the horizontal asymptote. Again, that is true for any functions like example 1 and 2 that we graphed that didn't have any vertical translation. But if you move it up or move it down, of course the horizontal asymptote will change. For this function that I just graphed, notice all the values will be greater than 5. So the horizontal asymptote will be at y equals 5. Because I added 5 to that function 2 to the x power. All right, the function passes through the point 0, 1, because if you raise anything to the 0 power, it's just going to be 1. Again, these are just, functions that are not really translated vertically. Didn't move up or didn't move down, then these will be true. But if you move your graph up or down at all, then these rules will slightly change. Okay, so let's look at some of these transformation rules. We know these rules already. Now, the horizontal translation, those happen within the exponent. Take a look. If you add a value, x plus h, and then we shift the graph y equals b to the x to the left h unit. Remember, adding inside actually moves it to the left, right? Now, what if you are subtracting a value in that power? Well, then we're translating that graph h units to the right. Okay, so the horizontal translation, something like this. If you have y equals 2 raised to the x plus 5, what will that plus 5 do? This graph is translated or moved 5 units to the which side? Left. Okay. Another example, what if you have y equals 7 raised to the x minus third power? Describe the translation for me. This is moved or translated. How many units? 3 units to the right. Okay? So if you're doing something in the exponent, those will make horizontal translation. Now, what if you are adding or subtracting to that term? So something like this. Let me write it. Y equals 2 to the x power, but then you're adding 7. Okay? Or y equals 5 to the x power, but then you're subtracting 10. What will happen? This graph will be translated, moved up 7 units. And then this one in the bottom, this one will be moved, what? Down 10 units. It's the same transformation rule that we went over in our very first unit. So let's fill this out and look at some examples together. So moving a k value, a constant k, will move the graph up k units. Subtracting k will move the graph down k units. So if you have an example like this, which got both going on, let's talk about the translation of this. Subtracting 4 will move the graph down 4 unit, right? That's going to be moved down 4. But if you take a look, we have plus 5. We have that 5 getting added to x in the power. So that will move 5 to the which side? Left. Give me just 1 second. All right, so let's identify the domain and range of this. Again, well, I'm just going to do A and B and then stop the video. Domain is going to be, even if you move it, it's still all real. Okay, domain is going to be all real. Now the range though, range is going to be different. Remember, range is usually from 0 to positive infinity if you didn't move it up or down at all. But notice we moved it down 4 units, right? Notice we moved it down 4 units. Therefore, the range will actually be from negative 4 to positive infinity. And you can check this by graphing it on a graphing calculator if you want to. But when you are finding the range, you just have to look at the vertical translation. Okay, let's do one more. This time looks like I'm adding 3, so this will move the graph up 3 units. But if you look carefully, we're subtracting 2 inside, so that will move 2 to the subtracting. This will be right. So let's write the domain and range. We just described the transformation briefly, but if I were to find the domain and range, well, of course, domain of any exponential function is always all real, but range is a little different this time, right? Range, notice that it moved up 3 units, so it's not going to be from 0 to positive infinity. It's actually going to be from 3 to positive infinity. If they ask you, hey, where is that horizontal asymptote? What are you going to tell them? Horizontal asymptote is at y equals 3. And for this one, A, we had a horizontal asymptote at y equals what number? -4. All right, so that's that's enough for the first half of 3.2. I will come back and go over the exponential growth and decay, the real world situation problems, a couple funny